So kind of piggybacking, nothing super new today. Maybe a little bit more reinforcement of yesterday's notes, but locating the absolute extrema of the function, if any even exists, over each interval. So this is like 4 different parts to the same problem. So on the first part, just notice that we're including the endpoints 1 and 4 with the brackets. On B, we're including the endpoint of 1, but not the endpoint of 4. Vice versa on C, and then on D, it's the open interval from 1 to 4, so we're not including either endpoint. So we'll do kind of the same thing for all of them. We'll come up with our critical points, starting with the endpoints, which depending on which part we're on, some of which we will be able to use and some of which we won't. But 1 comma something and 4 comma something. If you plug in 1, 5 minus 1 is 4. And if you plug in 4, 5 minus 4 is 1. And then from here, it's just taking the derivative. What's the derivative of 5 minus x? -1. So seeing at what location is this derivative going to ever equal 0? Never. At what location will it ever be undefined? Never, because it's a constant. This is a line, so there's no real fluctuation in the graph. So we get no additional critical points. So when we're answering these questions, for part A, when we can include both endpoints 1 and 4, the maximum is at 1, right? 1 comma 4. So the max is at 1, 4. And the min is at 4, 1. So I'm going to just do a quick sketch of this graph from 1 to 4. So the first interval, because it's closed, has a solid point at either end. So we have a max here and we have a min there. Easy enough? On the second part, part B, they keep it closed at 1, but it's an open circle at 4. So what does that do to our absolute extreme answers? What'd you say? Changes the minimum. The maximum is still the same. Agreed. The max is still 1, 4. What does it change the minimum to? You're just the idea guy. Good job. Well, you're right. The minimum does change. Can't be 4, 1 anymore because 4, 1's not in this interval. So what would we say the absolute minimum is? But then your next buddy would say 3.999999999. Right, does not exist. There is no absolute minimum point because even in that short little stretch of my line, you can get infinitely close to 4. And so when there's that infinite business going on, that minimum does not exist. So for part C, we're flipping that. This is an open circle. This is a closed circle. So Owen, tell me what the max and the min are. Yep. Max does not exist. Minimum is 4, 1. And then lastly, when they're both open circles, neither exists. There is no absolute max. There is no absolute min. No absolute extrema. Any questions on that? Okay. Number 2. We want to find our critical points. The intervals are not all -2 to 2 this time, so we're going to kind of have to change accordingly. But starting with points for part A, We do have an endpoint at negative 2 that's included, and we do have an endpoint at 2 that's included. What's the y coordinate that goes along with negative 2, Bryce L? I plug in negative 2. What's negative 2 squared? What? 4. What's 4 minus 4? 0. Square root of 0 is? Good. And if I plug in a 2, 4 minus 2 squared is 4 minus 4 is 0 also. That's just our endpoints. We also have to take our derivative. I'm going to rewrite my original as 4 minus x squared to the 1/2 power. So f prime of x equals, help me out, Elise. Someone carry on where she left off. Times negative 2x. Elise, tell me why they added that times negative 2x. Right, the chain rule. Yep. So now when I clean this up, the 2 and the 2 cancel. So I just have a negative x up top, and on the denominator I've got the square root of 4 minus x squared. So where will this derivative equal 0? A fraction equals 0 when the what is 0? The numerator. So this whole thing will equal 0 if the numerator equals 0, which is happening at an x equals 0. And a derivative is undefined when the denominator equals 0. So when I solve this, what does x equal? Plus or minus 2. Now those were already accounted for, because those were our endpoints. And so, and we're just on part A right now. If you plug in 0, what's your y coordinate? No. 2. 4 minus 0 squared? 4 square root of 4 is 2. So, on part A, what's our absolute maximum? 0, 2. What would you say about our absolute minimum? There's actually 2 absolute minimum points. There are 2 points that are the lowest. They're kind of in a tie. So we would say negative 2, 0, and 2, 0. We have 2 of them. Let's jump to part C just because it's the exact same as part A, except for the fact that it's now an open interval, so we cannot include the endpoint. So what would we say about our maximum? Still 0, 2. What would we say about our minimum? Good. Now when we jump to B, our interval is only going from negative 2 to 0. So which of these points am I now going to kind of not consider because it's not in our interval? 2, 0. So, and also I'm including the negative 2 endpoint and I'm not including the 0 endpoint. So what is our maximum? Does not exist. Good. And what is our minimum? Good. So the max would have been 0, 2, but the 0 end of this interval is open. Okay, in part D, we have to get rid of both of these points and take them out of oh no, not this one. We have to bring this one back into consideration, right? But we have to take out the negative 2, 0 and the 0, 2 from consideration because we're only going from 1 to 2. And so we have a kind of a new endpoint to search for, right? If the interval starts at 1, we have to find out where that point is at 1. What happens when I plug in a 1 to my function? Radical 3. I actually do take this out of consideration, right? Because 2 is an open endpoint here with the parentheses. So that's out of consideration. So what's my max? Yep. Max is 1 radical 3. And what's my minimum? Does not exist. Okie doke. So pay attention to your intervals, whether or not we're including endpoints or not. Understand what happens when it's an open interval and you're approaching an open circle, that absolute max or min does not exist. And we move down to the second type of problem that you'll run into on your homework. Sketch the graph of the function, then locate the absolute extrema over the given interval. So, piecewise function here. If we sketch this first piece from 1 to 3, it's worth finding your endpoints. If it starts at 1 and you plug in 1 here, where's that point? 1, so 1, 1, solid. And if you plug in 3, what are you going to get? 2 minus 3 squared. And that one's an open circle, yes? Now this is just to figure out how we're going to connect these, because it shouldn't be via a straight line. This is the same thing as negative x squared plus 2, right? So it's a parabola that's been flipped upside down and then shifted up 2, so there's sort of a slight curvature going on here. And then for 2 minus 3x, this is linear, so I can get the endpoint at 3, I can get the endpoint at 5, and I can just connect them with a straight line. So when x is 3, what's this? Negative 7 again, so that circle that was open is now getting filled up. And when I go to 5, where's the 5? 5, negative 13. 8, 9, 10, 11, 12, 13. So 5, negative 13, and that will be connected with a straight line. So obviously our endpoints, if you look at our critical points, the endpoints would be negative 1, 1, and 5, negative 13. Where is the slope 0 on this graph? I don't know. Good catch. 1, 1. Well done, Dan. That's right. Any place where the slope is 0 on this graph? Any place where the slope is 0? No. Any place where the slope is undefined on this graph? Yeah. Where did you say, Jenna? Right, at a sharp point. So that's worth looking at as a critical point, but obviously because we have a picture in front of us, we can see that the absolute max is at 1, 1, and the absolute min is at 5, negative 13. Again, you could do this algebraically, because you could find all those critical points based on the endpoints, and you could derive and set it equal to 0, set it equal to undefined. You could derive, set it equal to 0, and set it equal to undefined. The problem is you're going to never, well, you'll get a place on this one where the derivative equals 0, but it's not going to be in the proper interval, right? This parabola is eventually going to turn around, but you're going to get that derivative equals 0 at an x equals 0 coordinate, which is out of interval. And you won't necessarily get the undefined at 3, but you have to know that it's undefined at 3 because we're jumping from one graph to the other. So if the derivative at 3 here does not equal the derivative at 3 here, then there was no continuation of slope in your transition, and there was that sharp change of slope. Does that make sense? I will tell you, obviously, what's the derivative of this first piece? Negative 2x. So at the endpoint 3, this slope is negative 6 coming off of the parabola. But going into the line, the slope is negative 3, right? And so because of that drastic change there, you know, again, that fine balance between having your eye on like the algebra behind it, but also understanding how the picture, especially a piecewise function, plays into it. All right, let's jump down to the next one, which says to graph a function on this interval having these given characteristics. So we want to graph from negative 2 to 5 so that there's a relative minimum at negative 1, a critical number at 0, but not an extrema. So that means it's not a relative or an absolute anything. An absolute max at 2 and an absolute min at 5. Play with that for a minute on your own, and then I'll take a look at a couple of yours. Try to sketch a graph. We'll play teacher. If yours is good, we'll give you a point. If it's not, we'll play teacher. Actually, pick 3 numbers between 1 and 17. 2, 9, and 13. right, let's see what we think about, I don't know whose this is, but go through the checklist. Does he have, is this yours, Bryce? Does he have a relative minimum at -1? Yes. Does he have a critical number at 0, but not an extrema? No. So a critical number would suggest that the slope is either 0 or undefined there. So you could make it, you could do that. You see what I changed there? And kind of made it an undefined slope. You can do that. Or I could do the flip of that, and I could have made it like flat quickly and then go up. Then it would have had a slope of 0, but it wouldn't have been an extrema. Does he have an absolute max at 2? Yes. Does he have an absolute minimum at 5? Yes. And is his interval from -2 to 5? Yes. Pretty good. So just that one piece to change. Good job. Here is, does this person have a relative minimum at -1? Right there? Yep. Do they have a critical number at 0, but not an extrema? That's a relative extrema, right? That turned around. So again, we would need to do something like this where it kind of flattens and then carries on its way. That would change that. Kind of like this. It turns and then goes up. So it's going to produce a slope of 0, but it's not going to be a relative maximum because it increased going in and it's increasing coming out. Absolute max at 2 we have, absolute min at 5 we have. So again, it's that critical number but not being an extrema. That goes back to Jenna. And then we have Miss Emily's here. Relative min at -1. I see it. Critical number at 0 but not an extrema. She's got it. That's exactly it. Okay, she's got a slope of 0, but it's not an extrema. Good job. Absolute max at 2. Absolute min at 5. Shoot. We just needed this to go whoop, way down here, and then it would have been fine. All right, but we get the idea? Okay, flip to the back. Okay, true or false? If a function is continuous on a closed interval, then it must have a minimum on the interval. It's a closed interval, so no matter what we've got here, we've got to have solid endpoints. So there's a line, there's a parabola, there's another parabola. So if it's continuous on a closed interval, then it must have a minimum. I think that's true. The closed interval is the one detail there that's underratedly probably the most important, right? It's, it's one word, it happens quickly, but don't look past that. If x equals c is a critical number of the function f, then it is also a critical number of the function g of x, which is equivalent to the f of x minus k, where k is a constant. So let me ask you this. Let's take a function f, and let's graph it so it has a critical number at c. Right? Agreed? That is a critical number at a critical point at c. With a slope of 0. What happens, where's g of x relative to f of x? How many? K units to the right, we'll assume k is positive. Let's say it's k units to the right or k units to the left. Regardless, it's been shifted horizontally. So is that critical number, when we shift this horizontally, is it still going to be at C? No, then it is not necessarily also a critical number of the function g of x. So this is false. Okie doke. Yeah, your homework is just the odds in those sections. Obviously, we didn't get to that one example, but we did one similar one that we just didn't have time for both.